threshold or knee voltage, usually this we are getting a significant amount of current which is increasing very rapidly. Okay, and the behavior of the current, how the current and voltage is related in this region, in this basically this forward bias region, that is explained by this equation that is called the diode equation. Okay, where the diode current is equivalent to the reverse saturation current into e to the power b by eta Vt minus 1. So this Vt is the volt equivalent temperature or thermal voltage. Usually at room temperature, if you consider this value, if you calculate by putting the values of this both by putting the value of your temperature, that is at room temperature, if you take so if you consider at room temperature means usually we consider 27 degrees Celsius as the room temperature, and if you convert into the Kelvin, then temperature will be 300 degree Kelvin. Okay, so if you put this value, Bt is equal to that kT by Q. Okay, Bt is equal to this kT by Q. This is kT by Q. Okay, so this kT by Q, if you put the Boltzmann constant value as well as this Q value, that is the charge of the electron, and temperature at 300 degree Kelvin, if you put all this value, this Bt value comes to it is around 26. Just can you calculate this value? How much it is coming? Bt by Q, putting all this value. Usually this Bt is 26 millivolt, approximately 26 millivolt will obtained. This Q by K, if you take, this value will be, usually this Bt can also be represented as T by 11,600. This is 11,600. This is the value. So this Vt value, usually if it is given at the room temperature, directly you can put 26 millivolt for that Vt value. Or else if temperature is given, then you can calculate Vt is equal to T by 11,600. This is the value, this constant value, that is Q by K, this value will be 11,600. So by putting this value, you can get the result in the numericals. And this equation is valid for this forward bias characteristics where we get this value. Okay, so as we got this diode current, this ID is equal to I naught e to the power V by eta Vt minus 1. So this value, so usually this reverse saturation current, this I naught is very smaller than this your diode current ID, whereas this ID is in the range of some milliampere or few ampere, whereas this I naught is very in the range of some nano or picoampere you obtained the value of your I naught. So it is very much smaller as comparison to ID. So sometime we can have this value, this ID is equal to, if you evaluate this bracket, so this I naught into e to the power b by eta Vt minus I naught. So as comparison to this value is very small. So we can approximately take the value ID is equal to I naught e to the power v by eta Vt. So we can directly have the relation of this voltage and current, which is the exponential relation, because I naught is a fixed quantity. So it is the exponentially varying curve, this ID graph, this BI characteristics graph. So based upon the value of your temperature, it is varying. So how it is depending upon the temperature, you can evaluate from this equation. Okay, so this is about the forward bias characteristics of your PN junction diode. Let us come to the reverse bias. Reverse bias means just you have to give the reverse polarity. So in this graph, in the x-axis we are taking the voltage, y-axis we are taking the current. So in x-axis we are having the voltage, that is the forward biased voltage. This is the forward biased voltage. So according to you, according to that, you have to give the polarity, p side positive, n side negative. So this positive voltage we are applying. In the reverse bias case, so you have to give the just reverse of this voltage, so minus of whatever the vd we have taken, minus something we have to take, so just reverse the polarity. So in this reverse direction, whatever voltage we have taken, if you apply the reverse voltage and going on increasing the reverse voltage, so in the reverse bias, as we know, in the reverse bias condition we have seen that only due to the minority current the current conduction will takes place. So only the I0 will appear, or this reverse saturation or leakage current will appear. There is no forward current, and this leakage current range is very small. Okay, so here actually this graph, you just observe that in this id, this is in the milliampere range, this is only from this 0 to upward. Okay, in the positive axis this id is in the milliampere. In the negative axis, actually actually in the range of some very variable range is there, like it is you can see that for the gallium arsenide we are getting a 1 picoampere. Picoampere means 10 to the power minus 12, you just remember. Okay, so how much smaller amount of current we are getting here? We are getting in the range of, for germanium we are getting in the range of microampere. Okay, so this range is actually in comparison to picoampere, microampere is a very higher value. In comparison to microampere, milliampere is very higher value, so it is not possible to show in a single, in a constant scale. That's why this break points are given. Okay, we can break the axis. This break means within this range we take it in the range of picoampere, or we can break it in the range, in this range suppose we can take 1 picoampere, 2 picoampere, 3 picoampere, like that. And from, and just breaking this, and for this range we can take 100 picoampere, because it is difficult to show that 1 picoampere, 100 picoampere and 1 microampere in a single line. That's why this break is there. This distance is not uniform. Okay, so you should know that with the value how the current variation will be there. To show it in a two-dimensional small graph, only this breakpoint can be used. Okay, so so here we can see that as we are applying the reverse bias voltage, only a fixed amount of, small amount of current we are getting. This much of current for this gallium arsenide we are getting, or this much of current for this silicon diode we are getting. Throughout a small constant current we are getting. Okay, this is only the reverse saturation current, or I naught. Okay, I naught or reverse saturation current. So this reverse saturation current will not increase with increase in voltage, because this thermally generated carriers are fixed. Okay, we are not going on adding some more carrier, so due to that we are getting a fixed amount of current. But after, beyond the limit of voltage, you are going on increasing the reverse voltage again and again. After a particular limit, what will happen? Every device, every component is having its limitation. So after a certain voltage, after a threshold voltage, what will happen? It will enter into the breakdown region. Okay, this part of the graph is your forward biased region. Okay, this graph is for the forward biased. Okay, up to this much, this is the reverse biased part. And beyond this, where the, for this graph, this is the breakdown point. Okay, for this graph, this is the breakdown point. So the breakdown voltage will be different from different type of diode. So beyond this, we are getting the breakdown region. So what is breakdown region? After a limit of voltage, after, if you apply more voltage, then the diode enter into its breakdown region. That means the current will uncontrolledly, it will increase very rapidly, and it will increase to a very higher amount of current. Okay, very higher amount of current. So you can observe that almost vertically the current is increasing. What does it mean? That means the resistance, where there is resistance is 0. because we are getting a vertical parallel line with this current axis. That means the current is increasing, voltage at a fixed voltage, the current is going on increasing. Voltage is fixed, but current is increasing. So there is almost like zero resistance. So this breakdown at the beyond the breakdown region, the current will be very higher, and it will be a fixed amount of current we will obtain, but that current is not that is actually not the safe region for the diode, because very high current will flow means you can imagine what will happen to that particular device. It will burn out. If very high amount of current will flow through the device, then it will burn out. So in normal PN junction diode, after the beyond the breakdown region, we cannot operate the device or we cannot operate the diode. So for in the breakdown region operation, we usually specific diode is there, that is the reverse bias diode, or we can say Jenner diode is used. Okay, so we'll discuss the Jenner diode later on. So normal PN junction diode should be used under the region, that means the diode should not enter into the they should not enter into your breakdown region. So there should be a limitation. Okay, there should be a limitation. So that limitation is usually given by the manufacturer, which is called the peak inverse voltage. Peak inverse voltage. Peak inverse voltage, or it is called the PIV rating. PIV rating of the diode. So this is usually given by the manufacturer. That means what is the maximum inverse voltage applicable for this particular diode. That is always fixed in a diode. Beyond this peak inverse voltage, if you operate the diode, then it will be entering into the breakdown region and your diode will be burn out. Okay, so this PIV rating is usually given by the manufacturer. So PIV means the maximum reverse voltage that a diode can withstand without entering into the breakdown region. So for every diode, this PIV rating is fixed. It is given. Okay, so in the breakdown region, usually there is a range. Here it is noted down, like for germanium, what is the usually what is the breakdown voltage, for silicon, what is the breakdown voltage, for gallium arsenide, what is the breakdown voltage. So you can see that for the germanium, the less than 100 volt is the breakdown voltage is usually there. This is not this less than 100 volt means that is a not fixed value, for because it is why it is given less than 100 voltage. For some diode it may be 50 volt, some diode it may be 70 volt, it may be 80 volt, like that. So diode to diode, as per the manufacturer, it is different. So usually germanium is having a less value or less PIV rating in comparison to silicon and gallium arsenide. Okay, so in the silicon the range is 50 to 1 kilovolt, and this gallium arsenide also 50 volt to 1 kilovolt. So this range is different for every diode. So based on this PIV rating also, you can say that this diode is better than this diode. Usually there is a common question asked in Viva, why silicon diode is mostly preferred in comparison to germanium diode. One is that the material availability, whatever the temperature tolerance, all these things you can say. And also this is also one thing that PIV rating of your silicon is more than your germanium. So this can be, silicon diode can withstand a higher inverse voltage also. So this is also one factor of your why the silicon is mostly used. And also here something is given, that is the electron mobility, the ability of the electron to move. In case of germanium it is 3900, silicon it is 1500, gallium arsenide it is 8500. So mobility of your electron is more in case of your gallium arsenide, but this is specific purpose it is used. So usually we use the silicon or germanium diode. Okay.
Excuse me, ma'am.
And the threshold, yes.
Ma'am, I had a doubt, like what's the reason behind the difference in barrier potential for germanium and silicon? Like
This is the material properties. Okay, when we just understand the properties of that material, germanium and silicon. So why we can go for that structures and all these things. The material is having it is having more temperatures. Actually,
So,
practic. Yes.
I'm like, is it a trend like we go down the group, it decreases or something like that, or it's just like
Uh,
observational property?
you are saying about that periodic table group. You are saying that other for other material whatever we're using, na?
Yes, ma'am. Is it a trend or it's like something specific to these two elements only?
Uh, if you go inside the structure, then it can be confirmed. I'm not so much confirm about that whether for other material how it is behaving, but practically it is seen that if you practically analyze your silicon and germanium, usually these two are major dominating element. So we should analyze it. Uh, we should analyze it because nowhere I have seen that this other materials are the below elements are used as the semiconductor material. Obviously, this silicon and germanium as we are considering. So we have to go. We have to think that in germanium, usually what happen in comparison to silicon, one parameter, the most important parameter is temperature resistivity, the resistance of your how the material is resistance having the resistivity towards the temperature. So based on that mobility, all these things will depend. So I feel that based on that only the silicon the mobility is defined, and this silicon is having this type of property. So
Okay.
actually it is material related, more analysis is required. So those who are working on that particular material, then they can answer it better. So you can also search this whether it is applicable to other material or not.
Okay, ma'am. Okay.
It's a good question. It's this kind of things should be inputted in the mind so that we can think of it and we can have a new domain of research. So if you go to other material, then what actually we are focusing on silicon and germanium so that we are not going into that type of analysis, but it should be. So you just go through it. It's a good question. So you should just go through it. If you get any answer, then you can share with us.
So, ma'am, I searched the net before asking, but I couldn't find a like reasonable answer. There was no proper explanation.
Yeah, yeah. So actually, those who are using, those who are working in microelectronics domain, like inside structure of that electronics material or semiconductor material, they can answer it properly. So, okay, I can discuss with my colleague those who are working in that research domain. Okay. So actually, how this property is varying. Or physics people can give better answer. So if they will be using that, so we can get the answer. But your query is good. So where we were earlier. About that knee voltage, yeah. So for the silicon and for germanium and gallium arsenide, so other material also we can some research oriented paper I can find. So what will be the analysis of this knee voltage? So it's a good question. I will search the answer. Okay. Okay, so there are based on the VI characteristics of this diode, we can have just you can see that the diode characteristic. If you think this current is almost very small current, so it is almost negligible. So if you see ideally the characteristics, you can say at reverse bias the current is approximately zero, and in the forward biased mode currently after the threshold the current is almost very stiffly it is increasing, so we have a significant amount of current. So this behavior can be utilized as a semiconductor switch. That means whenever we want the diode to be switched on, then we have to forward bias it. If you want to make the diode switched off, then we have to apply the reverse bias voltage. This operation is called as your switching operation of your diode. So if you apply a particular amount of voltage, it will be utilized as a on switch, and if you applied a particular amount of voltage, can be utilized as the off switch. So that is called the switching characteristics of the diode. Yeah, so you can see that there are various characteristics of different type of diodes are there. So in our operation we have that p-n junction diode, this p-n junction diode, this kind of graph we are already discussed. So in Zener diode is also there in our syllabus. In detail we will discuss what is Zener diode, how it operates. So its behavior is like this. So usually in the normal p-n junction diode we operate the diode in the forward biased mode. In reverse bias mode, because beyond the PIV it is not possible to operate the diode because it will be damaged. So within this PIV range, the diode is having almost nil amount of current or zero amount of current, which is very small, or the reverse current is very less amount in comparison to your forward biased current. So usually forward bias mode is used for normal PN junction diode, wherever we are using. But in case of Zener diode, we have the utility of that Zener diode in the reverse region. Whenever we require a fixed amount of current for a particular voltage, maximum amount of current if you want, in that case we can use the Zener diode. So when we want to regulate the voltage, means whatever the amount of current will be there, but the voltage should remain constant. In that type of situation, we can use to regulate the voltage through the Zener diode. And some other characteristics, different diode has different type of characteristics. So only for the information I have kept these characteristics, but only for your operation, for scope of your syllabus, these two characteristics will be used, the PN normal diode and Zener diode. And other are only for your information. I have kept this from examination point of view, it is not required. Okay, so you can see that this is the diode where we are getting different kind of your LED is there. Okay, different type of different color LED is there. So different color LED, your graph characteristics will be different, the threshold voltage will be different. So this is the characteristics of your LED. Like this is the tunnel diode. Tunnel diode is a different type of diode, which is not tunnel diode. This above one is the tunnel diode. The characteristics is totally different. So the same diode is there, but its characteristics is different. Its construction is different. Its application is also different. So only PN junction diode, you focus on this PN junction diode and Zener diode. So this is about the characteristics of your PN junction diode. So one more thing is your ideal characteristics that I was asking. Okay, so when we think about the ideal behavior of the diode, so ideally means theoretically, if you apply a switching characteristics, or we can say switching characteristics of the diode. So in switching characteristics, if you draw the characteristics of the diode, if this is the voltage axis, this is the current axis. In that case, what we draw the diode characteristics, that means we apply after the threshold voltage, you just apply the current is increasing, and beyond the threshold the current is almost zero. This is the ideal characteristics, or we can say this is by considering the threshold voltage. Okay, by considering the threshold voltage or knee voltage. Suppose the diode, suppose this is the having the threshold voltage V threshold VTH, let's say, because VT is the volt equivalent temperature, so you will get confused. So to represent the knee voltage or threshold voltage, let us represent V threshold. So if the diode is having a threshold voltage, a particular amount of 0.7 or 0.3 volt of threshold voltage if you are considering, then the characteristics can be plotted like this. For ideally the characteristics could be like this. And also you can just take that, suppose this is the ideal diode. Okay, this is an ideal diode. Ideal diode means switching characteristics in ideal diode. Usually we imagine that threshold voltage is We assume that threshold voltage is 0. That means at the instant when the diode just enter into the positive, this is the 0 voltage, suppose this is the V volt, this is the I volt. If the diode is entering into the positive axis, that means 0 plus axis, then in this case the diode can be having a significant amount of current, that is the suppose this is the current, and at 0 minus the current will be almost 0. This is the ideal characteristics of the diode. You can follow this ideal characteristics. At the instant just we apply the positive voltage, 0 plus voltage, then the current is increasing, otherwise the current is 0. This behavior is called the ideal characteristics. Ideal characteristics of the diode. So in the ideal characteristics, what we assume that in forward biased condition, we take the diode is switched on, or it can be replaced by a short circuit equivalent. Okay, or it can be replaced by a short circuit equivalent, short circuit or on switch, in the on switch. In the reverse bias mode, if it is in the reverse biased condition, the diode is switched off, or the diode can be replaced by a open switch. The diode can be replaced by a open switch. So this is the switching characteristics of the diode. If we assume that the diode is having a ideal behavior, that means at the instant when diode enters into the forward bias region, we got a maximum current, otherwise the current will be 0. So whenever in the numerical, if it is mentioned that suppose in a circuit the diode is there, okay, suppose a particular circuit is there, and suppose this having some resistance, this is the diode, and we are applying some voltage, okay, and we have to find the, suppose this is the load resistance, we need to find the output voltage V naught here. So in this case you have to analyze that which kind of diode it is mentioned, whether it is mentioned that whether it is a silicon diode or germanium diode or any specific type of diode it is mentioned, then you have to apply the knee voltage. What happened?
Teacher, can you show that characteristics of diode slide again? Oh,
Yeah,
okay,
yeah,
I guess
just
browser isn't responding.
yeah. Okay, so in this type of situation, whenever a diode is given and it is not mentioned that whether it is a silicon diode or germanium diode. In that case, you have to consider the diode as an ideal diode, as an ideal diode. And in the ideal diode, you have to assume that when the diode is forward biased, the voltage drop across the diode is zero. That means directly you can replace the diode by a short circuit equivalent circuit. So, for example, for this circuit, suppose you are providing one alternating current, alternating voltage here. So, alternating voltage means this kind of voltage you are applying. So, it is having some positive half cycle, then negative half cycle, again positive half cycle, negative half cycle, that kind of thing is there. So, whenever the diode is entering into the positive half cycle, we have to assume that the diode is at the instant when it is just above the zero axis, then diode become forward biased, and we have to replace it by a simple short circuit equivalent. Okay, short circuit equivalent means this kind of things you have to do where the resistance is zero. Okay, and open circuit equivalent means simply open circuit where the resistance is infinite. Okay, infinite resistance you have to replace for the open circuit equivalent. So when the diode is in the forward biased mode, we have to replace the diode by short circuit, then solve the loop and find the voltage whatever we are getting at the end of your load. Then in the next instant, when the diode is reverse biased, simply replace the diode by open circuit. So if it is open circuit, then the circuit is not closed circuit, so the current will not flow through the circuit, so output voltage will be automatically zero. This kind of analysis you have to do if it is not mentioned that whether the diode is silicon or germanium or gallium arsenide or any specific notation is not given. Simply a symbol of diode is given. That means you have to assume that the diode is a ideal one, and we have to analyze in such a way that when it is mentioned that suppose the diode is a silicon diode, it is mentioned that above the diode it is written silicon diode. In that case, when the diode is forward biased, in that case we have to assume that the diode is the voltage drop across the diode is 0.7 volt. In that case, we can replace the diode. We can replace the diode by 0.7 volt. In that case, we can replace the diode by a 0.7 volt battery. Then put the other element of the circuit and calculate the load, whatever the voltage drop across this load. We will solve some numerical based on this. So in this way you have to solve. And in the reverse bias case, if it is mentioned silicon diode, then also you have to assume that it is open circuited. In the reverse bias mode, very little amount of current flows across the diode, so almost negligible or zero amount of, for simplicity we assume that zero amount of current is flowing. So zero current means zero voltage drop. So this can be replaced by an open circuit. So this is about the ideal characteristics of the diode. Okay, so based on this we will solve some numerical in the actually in the next class we will have solve some numericals only, so it may not be total 50 minutes, some earlier also we can complete it. Okay, so from 3 p.m. actually I have a meeting, so 3:30 we are having class. So if meeting will not be over, then little bit 5 to 6 minutes it's maybe later I will start, but I will try to join in time. So if the meeting will be over, and we will solve some numerical